Hello, differential equation students. Topic 5 is on linear first-order ordinary differential equations. A first-order ODE is linear if it can be written in the following way. Y prime is equal to some function of x times y plus some other function of x. Here, it's obvious that x should be interpreted as the independent variable and y as the dependent variable. If f of x is 0, so if this part here is not there in the equation above, then the equation is said to be homogeneous. Otherwise, it is inhomogeneous. Determine whether each ODE is first order and linear. If so, put it in the form mentioned above and characterize it as homogeneous or inhomogeneous. The first equation, let's first go through and talk about what order each of these differential equations is. So the highest derivative present will be its order. So looking at this first one, I see a y prime present, but no other higher derivative. So this is a first order. Second one, a y double prime exists. So this is a second order. Third equation will be a first order again. And the fourth one will also be a first order. The next, to determine whether the differential equation is linear. I'm going to go ahead and try to put it into this form that you see right here, and then we'll assess whether it's linear or not. So I'm going to isolate the y prime part. And I'm not going to bother doing this for the second order, because we're only interested if it's first order and linear, so this one is already sort of disqualified. Can't be both. Solving for the y prime, we get y prime is equal to, we have 2x, I'm going to do some rearranging of this term here and put the y squared second. So we have 2x y squared and then add an x. So from here we should be able to determine whether we have a linear equation by comparing it to the general form of a linear equation. So the a of x part, the coefficient of the y term, looks to be this 2x. And the f of x that's added at the end appears to just be this x. But notice, to be linear, you just have a y raised to the first, but here we have a y squared. So you might think, well, this doesn't appear to be a linear differential equation. What if you thought of it this way? Y prime is equal to 2xy, and that's my a of x times y plus x. If I try to write it this way, then you might argue, okay, we've got the f of x here, not a problem. We have a y, not a problem. And then this a of x we'll just say is this 2xy. But the problem with this is the coefficient of y has to be only a function of x at most, or just constants. There can be no y's involved. So this is not a workaround, if you will. This is a nonlinear differential equation. So this will disqualify this one from further analysis because we're only interested in the ones that are first order and linear. The second equation, we can skip that as well. Third one, I'm going to solve for the y prime. Y prime is equal to, we have 2xy and then add the x over. This one does fit the form of a linear equation. We have the a of x is just 2x times a y times the y there, and then plus an f of x, and the f of x is x. So this one is linear. It's already in the form that we have mentioned above. So now we need to characterize it as homogeneous or inhomogeneous. Well, f of x is present. It's a non-zero function. This is the f of x component. Because it's a non-zero function, we have an inhomogeneous differential equation. And the fourth one, solving for y prime, we get y prime is equal to just 2xy. This does fit the form described above. The 2x is our a of x function times y, and then plus, we can say the f of x is the zero function, which is allowed. These functions f of x and a of x could be constants, they could involve x, they could be 0. So this one is linear, and it's homogeneous, because the f of x function is 0. So the differential equations that were linear and first order are this one and this one, the third and the fourth ODE. Now, homogeneous linear differential equations are always separable. So this one the fourth one here is a separable differential equation. It'd be easy to separate the variables on this. You just have to divide, change the y prime to dy dx. I'll just illustrate that real fast. You'd have a dy dx equals a 2xy, divide by y, multiply by dx. So you have a 1 over y dy equals a 2x dx. And so you have the variable separated, and then you can integrate and proceed as instructed in the last lecture. The inhomogeneous ones are not always separable. Sometimes they are, sometimes they're not. So inhomogeneous, we'll say sometimes separable. Separable. And homogeneous is always separable. In this particular case, if we grab this one here and try to determine whether it's separable or not, if you factor an x out of the right side, you could write this as dy dx is equal to 2y plus 1, factor out the x, and then yes, you can separate the variables here. I would divide both sides by 2y plus 1. This is one way to do this, and multiply both sides by the dx, and notice we get separation of variables, and we can integrate both sides and proceed as instructed in the last lecture. But the question will be, what if we have a inhomogeneous linear first order differential equation, so like this third case here, but that is not separable? Then we need a tactic for solving such an ODE. So this topic, what we're going to learn today in topic 5, is how to solve linear inhomogeneous differential equations that are first order, that are not separable. Because if they are separable, we could go back to topic 4 and solve it. Now before we proceed, we're going to do a quick review of the derivative, the product rule, and then we're going to generalize the result. So if I want to find the derivative of a product e to the 3x times sine of x, then I employ the product rule. I do the derivative of the first function, so the derivative of e to the 3x, and to differentiate that, I need to use the chain rule. So we have to do the derivative of 3x first, which is 3, and then times e to the 3x. So here's the derivative of the first part, of the first factor, and then times the second factor, then plus, then the first factor, which is just e to the 3x, and then times the derivative of the second factor. And the derivative of sine of x is cosine of x. Now, to generalize this, suppose we have e to the f of x times y, and I say find the derivative with respect to x. Well, because we're doing a derivative with respect to x, and there's a variable y here, we're going to assume that that is a dependent variable on x, that it's an implied function of x. We're just using y to represent it. So we do the derivative of the first factor. Here's the split. The first factor is e to the f of x. And to do the chain rule on that, we have to differentiate the exponent first. So f prime of x times e to the f of x. So there's the derivative of the first factor times the second factor times y, plus the first factor, which is e to the f of x, and then times the derivative of the second factor. So I'll just put y prime there. Now I'm going to copy this and rearrange the terms. Doesn't really matter which one I did first because of the addition. And put it in this order just to have the y prime term first. And I'll explain why that is in a moment. So what we're going to be doing primarily in this section is trying to create this structure within a differential equation so that it can be reversed and written as a derivative of a product instead. So our goal here effectively is to go from this and convert it back to this statement. Notice that I can factor out the common e to the f of x, and what would be left would be a y prime plus f prime of x times y. This is going to be our starting point for a lot of differential equations. We're going to have a y prime plus some function of x times y, and we're going to want to determine what, we're going to call this thing here an integrating factor. I'll just go ahead and define that right now. This is called an integrating factor. We're going to have to determine that e to the f of x function, and to determine what f of x is, what this is, we're going to assume that the function we see here in front of the y is the derivative. So if we know what this function is right here, that's effectively our f prime. We'll do an antiderivative of it to know what f is. Then we're going to construct this integrating factor. We're going to distribute it through here so it looks like this statement right here, and then we're going to go backwards of the product rule and write our expression this way. So we'll be doing a lot of constructing of this structure so that we can go backwards on the product rule. Okay, here we go. So linear first-order ODEs can be solved with a method that uses an integrating factor to reverse the product rule, as demonstrated below. Okay, our first example. If I took this x here and added it to the other side, right, so imagine that's not there, and you put a plus x over here instead, do we identify this as, in fact, a linear first-order ODE? And the answer is yes. In fact, it happens to be this one right here. We've already established that that's linear in first order. Now, we also established that this was separable. So I could separate the variables here and use separation of variables, but I'm going to illustrate the new method. And this new method is important for those times precisely when you can't separate the variables. Now, I'm going to rearrange the terms around here a little bit. I'm going to put this part here, the f of x, back onto that side, but the part that has y involved, I'm going to move it back to the left to join the y prime. So this winds up reading y prime minus 2xy is equal to x. So I want the y prime and the y on the same side so that I can begin to mimic this structure right here. So notice that the y prime and the y are together. And then we have a plus f prime of x times y. So it's good to think of this subtraction here as adding a negative. So I'm going to do that instead. And then we have what we consider the f prime. So this right here is the f prime of x that's in this structure right here. So the next thing we have to do is determine what the integrating factor is. We have to come up with this e to the f of x component. So if f prime of x is equal to negative 2x, so f prime of x is equal to negative 2x, then f of x, do an antiderivative, would be negative x squared. And don't worry about the plus c at this stage. We just need to have any function that is an antiderivative of f prime, not the general. So the easiest one to go with is the one that has a 0 for the c. And then our integrating factor, is constructed by doing e raised to the f of x. So e to the negative x squared is our integrating factor. Okay, excuse me. Okay, so we have this structure in place, and we've just determined what the integrating factor is. Now we want to multiply this component by the integrating factor and distribute it so it looks like this so that I can use the reverse product rule. So I'm going to multiply both sides of my ODE by the integrating factor. So I'm going to first rewrite it. I'm going to go ahead and put the minus back there. So just instead of plus a negative, I'm going to say minus 2xy is equal to x. And we're going to multiply both sides by the integrating factor. When I do that, I get y prime e to the negative x squared minus 2x e to the negative x squared times y equals x times e to the negative x squared. Now when you do this process, the left side is always the result of a product rule. That product rule will always be the product of y times the integrating factor. So in other words, I can collapse this whole side to a derivative with respect to x of y times the integrating factor, which is e to the negative x squared. Let's just verify that real fast by doing the product rule. So if I'm going to differentiate this expression, I'll do the derivative of the first factor, that's y prime, check, times the second factor, check, plus, now this says minus right now, but plus the first factor, y, which is right there, times the derivative of the second factor. Well, the derivative of e to the negative x squared is itself times negative 2x. So that right there is the derivative of this factor. And because the derivative is negative, we can change the plus to subtraction. So yes, if I do the product rule on this product and differentiate that product, I do get this side of our differential equation. And the other side just stays the same. Okay, once you get to this point here, then you simply integrate both sides. So now we're going to integrate both sides. And I'll put our work up on over here in our space. So when you anti-differentiate a derivative, when you integrate a derivative, they just cancel each other and you get that product. You get y times e to the negative x squared. The other side we still need to integrate. We have to integrate x e to the negative x squared. So there's some work to be done over here. Sometimes this process gets jammed up right here when the integral that I just circled is very complicated or maybe even not doable by hand. So this process isn't guaranteed to always produce something we can complete by hand. But in this section, we only have problems that we can finish and see through. Integrate x times e to the negative x squared. Is this possible to do? The answer is yes. We need to do a substitution on the negative x squared, just a regular standard substitution. So the du will be negative 2x dx. So I'm going to do the construct the du process. So I'm going to put a negative 2 here and counter that with a negative 1/2, so that the negative 2x and the dx, all that stuff right there, just becomes my du. So we have y e to the negative x squared is equal to negative 1/2 integral of e to the u du. And that antiderivative e to the u du is just back to e to the u. This is where the plus c must enter, so that we can get a general solution. So we have negative 1/2 e to the u plus c. And go ahead and convert the u back to negative x squared. Oops. Let's do that again. Y e to the negative x squared is equal to negative 1/2 e to the negative x squared plus c. Now I want to complete, technically I'm done. This is an implicit equation. I want to make it explicit though, so I want to solve for y, get y isolated. So I'm going to multiply both sides, or divide both sides, however you want to think about this, but I'm going to multiply both sides by e to the x squared. The other option was to divide both sides by e to the negative x squared. And the reason I do this is because e to the x squared times e to the negative x squared, exponents add, you get e to the 0, which is 1, so you get y isolated. So we have y all by itself is equal to, and now we're going to distribute the e to the x squared on the right side. When you multiply e to the x squared times e to the negative x squared, so when you multiply these two things right there, again, the exponents cancel to 0, because you combine the exponents, you get e to the 0, which is 1. So we simply get negative 1/2 to lead off, and then plus, and then the other part has the c e to the x squared. Okay, so this is our general explicit solution. This is a general explicit solution. It's general because the c is still, we have, the c makes it general. It's explicit because y has been isolated. And now we have the information here that we want to construct a particular explicit function. So y of 0 is equal to 2. So I'm going to change y to 2 at the same time that I change all the inputs, which is x, to 0. So 0 squared. E to the 0 is just 1. So we get 2 is equal to negative half plus c. So add a half to both sides. And we get 5/2 is equal to c. So our explicit solution, particular solution, y is equal to negative 1/2 plus 5/2 times e to the x squared. And this is what we'll call our answer. It's a particular explicit solution. Be mindful in your homework, it may be that the homework will be satisfied if you give a particular implicit solution, meaning that the y is not yet isolated. In other words, you effectively start with this. You plug in y equals 2 and x equals 0 right here and solve for c, and then you replace the c and you write an answer that's still implicit, meaning the y's are not yet isolated. But for our lecture purposes, I will, as often as possible, continue to take our answers to functions of x where y is isolated. Okay, use an integrating factor to solve the ODE below. Verify your answer with technology. All right, so this one is throwing a curveball at us. X is now the dependent variable. Notice the x prime. And t is the independent variable. So hopefully that doesn't throw too much of a curveball at you. We're so used to thinking of x as independent, but now x is dependent and t is independent. I want to try to get it to the form where we have the x prime isolated. Keep in mind, I'm trying to reconstruct this form right here. So I want the x prime, which is now taking the place of the y prime. I want the x prime to be isolated, and then I want to see some sort of function coefficient of just x. Of course, this will be a f prime of t, and this will be an x in this case. So I have to divide both sides by the 1 plus t to begin. So we have x prime plus 1 over 1 plus t times x, I'll write it like that, is equal to cosine of t over 1 plus t. So now this side, right here, mimics this side, or this expression. So we want to interpret the coefficient of the x as a derivative with respect to t, and then construct the integrating factor next. So our f prime of t is equal to this 1 over 1 plus t. So that means f of t, we've got to do an antiderivative here. The antiderivative of 1 over 1 plus t is the natural log of the absolute of 1 plus t. This is the most general antiderivative. We could go ahead and make an assumption that 1 plus t must be positive and not deal with the absolute values on this. Say f of t equals natural log of just 1 plus t. All that matters is that I find any function whose derivative is this. So this function, even without the absolute values, the derivative of natural log of 1 plus t is 1 over 1 plus t. So without the absolute values, we should still be able to push this through with our integrating factor. So let's construct the integrating factor next. It's going to be e raised to the f of t, so e raised to the natural log of 1 plus t. But you might remember your properties that when you do e raised to the natural log, they cancel each other. So in this case, the integrating factor just becomes 1 plus t. So it means I need to take this expression right here and multiply both sides by this integrating factor, which is 1 plus t. And notice what happens. It takes you full circle right back to where I started with. When I multiply everything by 1 plus t, I get 1 plus t times x prime plus just x equals just cosine of t. That is precisely where we started. Which means that I should have recognized this left side as already a result of a product rule. It was already of the form a result of a product rule that I could reverse into a derivative of a product. So this side will condense to the derivative of, with respect to t, of the dependent variable, which is x, times the integrating factor, which is just 1 plus t. So you could write it this way. Doesn't matter which order you write those two factors in, but we have a derivative of x times 1 plus t. Let's check it using the product rule. The derivative of the first factor, derivative of x, is x prime, times the second factor, check, plus the first factor, x, right, which is right there, times the derivative of the second factor. And the derivative of 1 plus t is 1, so check. Okay, now I want to integrate both sides again. Right, copy those instructions. We do that same thing next. And let's put our result over in the next column. So here's a derivative. If you integrate a derivative, they cancel each other. You can just get x times 1 plus t equals. And the other side of the differential equation, here we still need to integrate, so I'll write this down, the integral of cosine of t dt. So we get to this point. The left side is considered integrated already, and by the right side we need to integrate. Antiderivative of cosine is sine of t, and then plus a constant. The constant must show up at this point. And then we finish this by dividing both sides by 1 plus t, so we get the x isolated. And here is our explicit general solution. It's explicit because we've isolated the dependent variable x, and it's general because of the c. Now let's do the initial condition. X of 0 is 3, so I can change x to 3 at the same time I change all the independent variables t's to 0. Well, sine of 0 is 0, so the top just becomes c, and the bottom becomes 1, so we get cleanly that c must be 3. And so our final result, the particular solution that's explicit, is x is equal to sine of t plus a 3 all over a 1 plus t. We're going to verify our answer with technology. Now I'm going to go straight to Wolfram Alpha to do this. And I typed in, I've done this already ahead of time, I'll show you in a moment, but I just typed in solve, I typed in that differential equation exactly as I see it, comma, and then I put the initial condition. Let's go ahead and go to Wolfram so you can see that. You'll notice I did, on the cosine part of this, I did have to put the cosine of and use parentheses there. Wolfram likes you to use parentheses around the argument of your trig functions. But everything else I just typed in exactly as I saw. And this is giving a, for some reason does not look normal right now, so let's have it reload. Okay. So you can see that it's interpreting it correctly. Notice it puts, when it says the input interpretation area, it says 1 plus t times x prime of t. So it's recognizing that you're trying to say x is the dependent variable and the independent variable is t. So it's putting that of t next to the x prime and next to the x as function notation. That's not saying x prime times t, it's saying x prime of t as function notation. So everything's interpreted correctly, and then our solution I'm not seeing the solution. Let's hit return again. Oh, there's result. For some reason, when I zoomed in, that seemed to have vanished. And the result is x of t is equal to sine of t plus 3 all over t plus 1. So that happens to match exactly what we have here. Sine of t plus 3 all over t plus 1. Okay, let's go to the next one. Use an integrating factor to solve the ODE below. Verify your answer by hand this time. And this time there's no initial condition, there's no point, so we're going to have to settle with the general solution. This time, with a little bit of foresight, I recognize that we have the y prime and the y, and the functions next to it are, one is a derivative of the other. So I already recognize that this is the result of a product rule. If I go through the process of constructing the integrating factor and then multiplying both sides by the integrating factor, you're going to wind up going in a circle again, just kind of like we did in the last example. So this already collapses to a derivative of the dependent variable y times x squared. X squared would have been our integrating factor. Let's just verify that real fast. Using product rule, the derivative of y is y prime, check, times the second, check, plus the first, y, which is there, check, times the derivative of the second, which is 2x, check. So we do definitely recognize that this is already the result of a product rule. Equals secant of x. I'm going to integrate both sides. So integrate the derivative gives us y times x squared. And integrate the other side still needs to be done. And the antiderivative of secant of x, this is one you should have learned in a Calc 2 class. It's the natural log of the absolute value of secant of x plus tangent of x. And here's where the plus c shows up. And finally, this is an implicit. Let's go ahead and get an explicit and get y by itself. Y is equal to the, I'm going to just copy this, all of that, divided by x squared. Make sure the division, the plus c is part of the numerator. It'd be incorrect for you to think later at the end, oh, I forgot my plus c. I'm going to put it on right here at the very end. This would be incorrect. The plus c must surface precisely when you do this antiderivative. That's when you need to get the plus c. And then any solving for y after that, sometimes that c can't be ignored and then put at the very, very end again. So the plus c is part of the numerator. Okay, now this one we're expected to verify by hand. There's no information here to give us, to have us solve for, move that over just slightly, to have us solve for c. So we're just going to do the derivative exactly as we see it, and plug in the derivative right here, plug in the original right there, and just see if this differential equation is in fact satisfied. So I have to do y prime. Now this function is a quotient, so I'm going to do the quotient rule. I'm going to have to do the derivative of the numerator. So we have to do the derivative of this natural log of secant x plus tangent x. That should just take us back to secant x. Well, let's verify that using our rules about differentiating natural log of an argument. The derivative of natural log of an argument is the derivative of the argument over the argument. In other words, the derivative of natural log of u is u prime over u. So when I'm differentiating the top as part of my quotient rule, I need to differentiate this natural log expression. So the derivative of natural log secant x plus tangent x is, we put the argument in the denominator, and then the derivative of the argument in the numerator. So the derivative of secant is secant tangent, and the derivative of tangent is secant squared. So there's the derivative of the natural log part. The plus c will go to 0. So there's the derivative of the entire numerator. But now we say times the denominator minus. Then we do the numerator times the derivative of the denominator. Oh, I forgot to put a square here. Times the denominator. Let's go ahead and put the derivative of the denominator first. And now let's rewrite the numerator, which is natural log absolute secant x plus tangent x, and then the plus c. So there's the entire numerator. So there's my result using the quotient rule, at least part of it. And then, of course, all of this is over the denominator squared. So all over x to the 4th. And here's the quotient rule used in its entirety. Well, for our sake, let's see if we can't simplify this a little bit before we go plugging this in to this differential equation and see if we get a satisfied differential equation. If you notice here, if you factor out one of the secants, then you'll be left with the tangent plus secant, which cancels with the secant plus tangent in the bottom. So we do, in fact, get very nice cancellation or simplification of this back to secant, which verifies that the derivative of natural log of secant x plus tangent x does just go right back to secant, which is why the antiderivative of secant is what it is. Okay, so let's go ahead and do that. So y prime can be written instead as just, I'll put the x squared first times secant of x. If it's helpful, let's go ahead and distribute the negative 2x. So we have negative 2x, natural log, absolute secant x plus tangent x, and then minus 2xc. So I distributed the negative 2x. This is all over x to the 4th. So a few different options here. We could leave it all over x to the 4th. Let me look ahead and see what's going to happen here. We're going to multiply y prime by an x squared. Let's go ahead and just put this all over x to the 4th. The other option is to split up the x to the 4th. In fact, I'm going to do that and then simplify these terms. All right, so I'm going to put this over x to the 4th, and then we get some simplification here for this fraction. So let's go ahead and do that over x squared. Put the middle one under x to the 4th, so that 2 will not be needed, and we'll have over an x cubed. And the last one will be, this x isn't needed right there. Did I say the 2 wasn't needed? I meant the x wasn't needed. And this one over x cubed as well. Okay, so here's our y prime. And then here's our y. Okay. So I'm going to substitute y prime into the y prime there, and y into the y there, and then work this side and see if in the end it just boils down to secant of x. All right, so we have x squared times y prime. Okay, so I've done this part, x squared times y prime, plus 2xy is next. So plus 2x times y, and y is right there. And let's see what this becomes. Okay. Distribute the x squared. So we get a nice clean secant x to start, minus, distributing the x squared is going to, we're going to leave, that's going to leave an x down in the denominator here because there's an x cubed, so it's going to be minus 2 over x times the natural log of absolute secant x plus tangent x. And then minus, distribute, it's going to be minus 2c over x. Okay. Plus, now distribute the 2x here. Well, this x will cancel with one of those x's down here, leaving an x under both this, and then the 2 will distribute. So we're going to have a 2 over x times natural log of absolute secant x plus tangent x, and then plus a 2c over x. Now notice what cancels? Those are gone. Those are gone. And in the end, we just get a clean secant of x. So we just verified that given this function y, when you find its y prime, and you plug y prime and y into this differential equation right there, in particular, that we will simplify to secant of x. So we've shown that this is, in fact, a solution. So here is our general explicit solution, verified by hand. Let's go to the next one. Last slide. Use an integrating factor to solve the ODE below. Notice that this equation is also separable, so we're going to solve it both ways, separation of variables and using integrating factors. This is already in the form I want it to be. By the form I want it to be is referring to right here. We have y prime isolated plus some sort of function of the independent variable times y. Now in this case the independent variable is t, not x, but we certainly have that structure right there. So the f prime of t is the sine of t. That's next to that. That's being multiplied with that y. It's this one right here. And just a coincidence, it's the same as that. But this is the one I'm focused on. F of t, therefore, do the antiderivative of sine is negative cosine. You don't need the plus c right here. We should need any function that's an antiderivative. And so our integrating factor, just to stick with the same color coding I've been doing, the integrating factor is going to be e raised to this f of t function. So e to the negative cosine of t. Now we want to take our differential equation and multiply both sides by this integrating factor. So we have y prime plus y sine t equals sine of t, and multiply both sides by the integrating factor. Oops, I forgot that should be this. Here we go. Integrating factor gets multiplied both sides. Distribute. So we have y prime e to the negative cosine t plus, I'll put the sine of t times e to the negative cosine of t times the y. Doesn't really matter the order I write those factors in. And the other side is going to be sine of t times e to the negative cosine t. This will always be the result of a product rule, and that product will be the derivative with respect to t of the dependent variable times the integrating factor. Let's just verify this. The derivative of the first factor, check, times the second factor, check, plus, check, the first factor, check, times the derivative of the second factor. And using the chain rule in this, the derivative of e to the negative cosine t is itself, times the derivative of negative cosine t, which is sine t. So check. Now we want to integrate both sides. So we get the integral of a derivative just cancels each other. So we get e to the negative y times e to the negative cosine of t is equal to, and now we want to integrate this side still. With respect to t. Give myself a little more space. Let me put this work there and move this up. I would like to finish all this in one column. To complete this integral here, right there, I need to do a substitution on this exponent. So I'm going to let u equal negative cosine of t. Therefore, du will be sine of t dt. And we already have a sine of t dt right there, so that we can construct the du right away from this. Okay, so rewriting the left side, that's done, equals, this will just be an integral of e to the u du after I do that u substitution, which gives us an answer of just e to the u. And then do the back substitution, e to the u, so it's e to the negative cosine of t. Don't forget the plus c needs to surface at this point. And then finally, I want to multiply, or get the y by itself, so I'm going to multiply both sides by e to the positive cosine of t. That'll get the y isolated. So we have y is equal to e to the negative cosine t times e to the positive cosine t. So when I multiply those two things, I get just 1 plus c e to the cosine of t. Okay, so here is the best we can do, because we don't have any conditions here to determine what c is to find a particular answer. So there's my general explicit solution. Now let's do this with separation of variables. Now this particular one, I'm going to now move the y back to the other side. So we have negative y sine of t plus sine of t. This is an inhomogeneous because we have a function of t here off on the side. So if you go back to our definition or our general form here, right, there's a function of the independent variable that's sort of isolated, and then a coefficient function of the independent variable multiplied by the dependent variable here in the front. So in this case here, we can see that our f of t is right there, and then our a of t is this negative sine t. So this is our linear differential equation. It's inhomogeneous because this part here is non-zero. It's present. And inhomogeneous means sometimes they're separable. And this is the case where it happens to be separable. Homogeneous will always be separable. Inhomogeneous is only sometimes. And this is one of those times. Because if I factor out, I'm going to factor out the negative and the sine of t. So it reads this way. I'm going to write this y prime as dy dt. Factor out a negative sine t. So that leaves us a y minus 1 times a negative sine t. The reason I factored out the negative is because I prefer to keep a positive coefficient on the y. Oops, what is happening here? Go away, please. Now let's go ahead and separate the variables. I'm going to divide by y minus 1, and then times dy is equal to negative sine of t times dt. Integrate both sides next. Antiderivative of 1 over y minus 1 is natural log of absolute y minus 1 is equal to antiderivative negative sine t is cosine of t plus a constant. Now I want to exponentiate both sides. This is an implicit answer. I want to get to an explicit answer. So I'm going to do e raised to each side, and e raised to a natural log cancels, so we get just absolute of y minus 1. And here we have e to the cosine of t, and then you can break off the plus c in the exponent as times e to the c. Then you can get rid of the absolute value by creating a plus minus. Put the e to the c first, and then the e to the cosine t next. And this plus minus e to the c is just another arbitrary constant. So we can just make that a c again. Or call it a different letter. If you don't like abusing using c every time we have a general constant, I get that, because this c should not be thought of the same as the value as that c. But anyway, we can use c or a different letter. Maybe we can call that a just to avoid that confusion, a capital A. So there's our arbitrary constant. Now we've got to add 1 to both sides, and notice we get y is equal to 1 plus some constant times e to the cosine of t. And this is the same result we got using an integrating factor. Same general solution. Different letters to represent the arbitrary constant, but it's the same general solution. And that wraps up our lesson on topic 5.